Now, discussing the other LMS based adaptive filters requires a background of what exactly the LMS algorithm is there. This we have already covered into one of our previous video into the same chapter here, and the most important, that is the normalized version of the LMS algorithm thereupon we have addressed here. See, for the practical applications, there is a continuous research going on to provide more and more efficiency here. So, number of times a lot of modifications are made to the original contribution. So here it is for the LMS algorithm here, and the study is a continuous here. For achievement of greater efficiency here, most of the time modifications with one or two parameters are focused here. So in this regard, we have the brief overview of the three types of the modifications. First one includes the Leaky LMS algorithm, that is for dealing with the problems that occur when the autocorrelation matrix is a singular matrix type here. Next one, we have the block LMS algorithm and the sign algorithms for increasing the computational efficiency of the LMS algorithm here. And at the last, we have the third type, that is the variable step size, that we can abbreviate to as capital VS algorithms for improvement of the speed of the convergence here. So let us first of all address the first type of the LMS algorithm, that is the Leaky LMS algorithm here. LMS standing for the least mean square algorithm here. Now see, when the input discrete time random process, that we generally denote by x of n here, so it is input to the adaptive filter. The block schematics we have also seen in the previous video where application of noise cancellation was discussed here. So thereupon it will be the autocorrelation matrix into the use with zero eigenvalues, and the LMS adaptive filter has one or more modes that are undriven and undamped here. So let us for example see that if we have lambda suffix k is equal to 0, so this is for the eigenvalues, the representation. So that time the expected value of u suffix n of k will be equal to u suffix 0 of k here. So this does not decay to the 0 value with the n here. Since it is possible for these undamped modes to become unstable, it is quite important to stabilize the LMS adaptive filter by forcing these particular modes to the value 0 here. Now there it is one solution or one way to have accomplishment of this particular task, that is to introduce a leakage coefficient. See, the leakage coefficient can be denoted in the earlier expressions of the LMS algorithm by the Greek symbol gamma. So the LMS algorithm, with the help of representing the leakage coefficient new one represented by gamma, will be of the form, here we have w suffix n plus 1 is equal to 1 minus mu into gamma. Mu is the step size, gamma is the leakage coefficient newly introduced here. So 1 minus mu into gamma, this bracket is multiplied by the weight w suffix n. This is further added by the second term where we have mu in multiplication to e of n, further multiplied to the complex conjugate of the original signal x of n here. See, the value of the leakage coefficient gamma is always greater than 0, whereas it is very less than that of the 1 here. Now you see the effect of making the use of the leakage coefficient gamma here is to force the filter coefficients to the value 0 if either the error signal denoted by E of n or the input signal that is the discrete time random process x of n, will become 0, and to force any of the undamped modes of the system to zeros here. Now you see, the properties of the leaky LMS algorithm may be derived by examining the behavior of estimate of the weight vector that we have denoted by capital E of W suffix n here. Now, if we make a simple substitution to our previous expression of the error signal E of n into the previous expression here, so that time we have W suffix n plus 1 is equal to, we have capital I minus mu times conjugate of x of n into the transpose of x of n added by gamma into capital I. This square bracket is multiplied by the weight vector W suffix n, further added by mu into d of n into the complex conjugate of x of n. Now, taking the expected value on the both the sides and making the use of the independence assumption, we get the new form of the expression, that it is capital E of W suffix n plus 1 is equal to, we have in the square bracket I minus mu times the autocorrelation matrix Rx added by gamma, the leakage coefficient, multiplied to capital I here, and this square bracket after closing is multiplied to the expected value of the weight vector W suffix n here. Further, the last term is added on to the RHS, that is equal to mu into the cross correlation small r suffix dx here. Now, if we have comparison of this particular expression to whatever we have learned in previous understanding of the LMS algorithm here, we see that the autocorrelation matrix Rx into the original LMS algorithm has been replaced here with the autocorrelation matrix Rx added by the leakage coefficient gamma multiplied to capital I here. So therefore, the coefficient leakage term will effectively add white noise to the signal x of n by adding gamma to the main diagonal of the autocorrelation matrix here. And since we know that the eigenvalues of this Rx plus gamma suffix gamma into capital I are lambda suffix k added by gamma, and since lambda suffix k the eigenvalues are always positive, that means greater than or equal to 0, so then none of the modes of the leaky LMS algorithm will be undamped, and in addition the constraint onto the step size, that is denoted by mu, for convergence of the algorithm in the mean becomes mu will be greater than 0, but it will be less than 2 divided by lambda max added by the leakage coefficient, that is denoted by small gamma here. Now there is one drawback to this leaky LMS algorithm, that is, for the case of stationarity into consideration here, the steady state solution will be a biased one, it will not be the unbiased one. Specifically, if we note the weight vector W suffix n converges into the mean, so that time we have the limit n tends to infinity for the expected value of W suffix n, that is equal to inverse of the parenthesis where we have the autocorrelation matrix capital R suffix x added by gamma into capital I is multiplied to the cross correlation small r suffix dx here. So therefore, the leakage coefficient will introduce a bias into the steady state solution here. Now for minimization of the error, the leaky LMS algorithm may also be derived by making the use of the LMS gradient descent algorithm. So here we have minimization of the error denoted by zeta of n, that is equal to mod square of E of n added by gamma, the leakage coefficient, multiplied to double mod square of W suffix n here. Now, since the gradient of zeta of n, here we denote with the help of del zeta of n, that is equal to minus of the error signal E of n into the complex conjugate of x of n added by gamma into w suffix n. So that time the gradient descent algorithm will take the form that we show mathematically. On the left hand side we introduce w suffix n plus 1. This is equal to w suffix n minus mu multiplied to the gradient zeta suffix n, here zeta of n, which is equal to w suffix n minus mu into gamma times w suffix n added by mu into E of n into the complex conjugate of x of n here. So here it is a complete discussion with respect to the first type of the LMS algorithm that it was remade to be addressed here. So this was the leaky LMS algorithm here. Now we are going to have a discussion on to the LMS algorithms with the reduced complexity here. So this is the second type out of the 3 topics to be addressed in this particular video here. See, while designing any of the engineering system, always and always there is a focus on its complexity here, and we always expect the system to be designed, developed with the least complexity here, so that we have the good efficiency achieved here. So of course we want the LMS algorithm with the reduced complexity also, that is requirement of many of the practical applications here, such as the high-speed digital communications here. So there are several of the approaches that may be utilized to have reduction into the computational requirements of the LMS algorithm here. If we talk about the one where the block LMS algorithm having the identicalness to the LMS algorithm, except that the filter coefficients are updated only once for each block of capital L samples here. So in other words, we can say that the filter coefficients are held constant over each block of capital L samples, and the filter output that generally we denote by y of n and the error signal E of n for each value of small n within the block are calculated using the filter coefficients for that particular block here. So therefore at the end of each block, the coefficients are updated using an average of the L gradient estimates over the block. So here we have the update equation for the coefficients into the kth block. It is w suffix k plus 1 into capital L here. So capital L should be there into the suffix in multiplication with the bracket k plus 1 on the left hand side here. So this is equal to w suffix k into capital L added by mu into 1 by capital L multiplied to the summation where the index variable small l ranges from 0 to capital L minus 1 for the product of E of k into L added by small l multiplied to the complex conjugate of x of k into capital L added by small l here. So here output for the kth block can be given by the expression. The output is of course denoted by small y. Here we have small y of k into capital L added by small l. This is equal to the weight transpose. So here we have in the power capital T to the weight representation w in the suffix k into capital L here. This is in multiplication to x of k into capital L added by small l. So the small l here will range with the values 0, 1, 2 and so on up to the maximum capital L minus 1. So here the error signal can be denoted as E of capital L multiplied by small k added by small l is equal to the desired form of the signal d of k l added by small l minus the transpose of the weight w suffix k into capital L multiplied to x of kl plus l. So where L small will have the usual notations. The values will be ranging from 0, 1, 2 and so on up to capital L minus 1 here. Now since we have the output y of n over each block of L values, and that is the convolution of the weight vector W suffix KL with a block of the input samples, the efficiency of the block LMS algorithm comes from using the fast Fourier transformation to perform this particular block convolution. Now, for reducing the complexity of the LMS algorithm, there it is also another approach here. With the help of this particular approach, the LMS algorithms are also known by the name sign algorithms here. Basically, in these particular algorithms, the LMS coefficient update equation is modified by application of the sign operator to either the error signal E of n and the data signal x of n, the input, or both of these error signal and the data signal here. So for example, let us have assumption that x of n, the signal to be fed as input, and the desired signal d of n to be extracted from it are the real valued random processes here. The sign error algorithm will be having this particular mathematical form here. W suffix n plus 1 is equal to W suffix n added by mu into SGN of the error signal E of n multiplied by x of n here. So here SGN of E of n here, the standard type of the signal we have already discussed in the first chapter here. This is supposed to opt with only the three possibilities where we have the positive 1 value when E of n is greater than 0. When E of n is equal to 0, we have it equal to 0, and it will have minus 1 value for E of n less than 0. So this is the signum function here. Now the sign error algorithm is also possible to be derived by the use of the LMS gradient descent algorithm for minimizing the error, denoted by zeta of n is equal to mod of the error signal E of n here. So for this purpose, let us have the partial differentiation. Here we have del omega suffix n of k here for the mod of error E of n to be the signum function of E of n multiplied by the partial differentiation del W suffix n of k or E of n. So here we have signum function of E of n into x of n minus k here. So therefore the gradient vector will take the form del zeta of n is equal to the signum function E of n into x of n here. X should be a small casing here, the type of mistake here. So this is what the result here, and therefore the sign error algorithm is also sometimes known by the name least mean absolute value algorithm here. We can abbreviate it to as capital LMAV, standing for least mean absolute value here. So this was the example where we have made the use of the error signal with the help of the signum or the sign of the error here. Now in order to bring the computational complexity reduced here, we have one simplified way of using the sign of the data signal also. So this is possible for the data signal, error signal, or both the signals here. So for the data signal, making the use of sign here, we have the algorithm described as W suffix n plus 1 is equal to W suffix n added by mu times the error signal E of n into the signum function of x of n here. So this is the sign data algorithm here. Now we can note one thing, that the kth coefficient into the sign of the data vector may be written to the form we have signum of x of n minus k is equal to x of n minus k divided by mod of x of n minus k. So therefore, as in the case of the normalized LMS algorithm, NLMS algorithm, where the weight vector is normalized by double mod square of x of n, the sign data algorithm will individually normalize each of the coefficient of the weight vector. So therefore, the sign data algorithm can be rewritten as w sub n plus 1 of k is equal to w sub n of k added by mu divided by mod of x of n minus k. This ratio is multiplied to e of n into x of n minus k. So this is the LMS algorithm that has a different step size for each of the coefficient in the weight vector here. Now at last, quantization of both the error and the data signal together will lead to the sign algorithm. So this is the use of signs for the two cases here, one for the error and another for the data here. So this has the coefficient update equation given by the mathematical expression that you can outline here. So here we have w suffix n plus 1 is equal to w suffix n added by mu multiplied to the signum function sgn of e of n multiplied by sgn of x of n here. So as in the previous case, we have been introduced to the leakage term denoted by gamma here for bringing stability into the current case here. Most of the times for sign algorithm, the update equation practically is given by this expression where we have w suffix n plus 1 is equal to 1 minus mu into gamma, where gamma is the leakage term here. This bracket is multiplied to the weight vector w suffix n, further added by mu into the signum function of e of n into the signum function of x of n here. So this was all about the second type here for reduction into the computational complexity here. Now we are going to have brief discussion with respect to the third and the last type to be discussed. So that it is for the variable step size algorithms here. Now as we have seen into the mathematical expressions describing the LMS algorithm, there it is the use of step size denoted by mu here for selecting the step size into the LMS algorithms. There it is a balance or what we can say a trade-off between the rate of convergence, the amount of excess mean square error, and the ability of the filter to track signals as their statistics will change here. Now for the very ideal case, the adaptation will begin and the weight vector w suffix n is very far from the optimum solution. The step size here should be very large in order to have movement of the weight vector rapidly towards the desired solution here. And then as the filter begins to converge into the mean to the steady state solution, the step size should be decreased in order to have reduction into the excess mean square error. So from this, one observation can be made that the possibility of using a variable step size into the LMS adaptive filter is there, and that we are going to focus. That is why the third type of the LMS adaptive based filters here, so that it is variable step size algorithm. So let us assume here that we have x of n and d of n, x of n the input signal having the desired signal component and the noise component here, whereas d of n is the desired signal. So these are the real valued processes, and one approach that we have for changing the step size to be referred to as variable step algorithm, what we have abbreviated as VS algorithm. In the beginning also I have introduced you to this particular abbreviation here, and here it is to make the use of coefficient update equation having the mathematical form W suffix n plus 1 of k is equal to W suffix n of k added by mu suffix n of k into the error signal E of n into x of n minus k here. So in this representation, mu suffix n of k is representing the variable step sizes, and these are adjusted independently for each of the coefficient value here. The rules for making the adjustments to the step sizes are tied to the rate at which the gradient estimate will change its particular sign here, and with the estimated gradient given by the expression, here we have the gradient square of the error signal E of n. It is equal to minus 2 multiplied by E of n into x of n minus k. So these rules are based on the promise that if the sign of error signal multiplied by x of n minus k is changing frequently, then the coefficient W suffix n of k should be close to its optimum value where the gradient is equal to 0. So if the change of the sign is not observed to be a frequent and even here, so that time the coefficient denoted by W suffix n of k is probably not very close to its optimum value here. So therefore additionally we have the hard limits placed onto the step size. Here we denote the variable step size mu suffix n of k greater than mu suffix min, the minimum, whereas it is less than mu suffix maximum, and this is in order to ensure that the VS algorithm, variable step algorithm, will converge into the mean with only modest increase into the computation, and the VS algorithm may result into a considerable improvement in the convergence rate here. So this was all about the other LMS based adaptive filters here. The three types we have discussed so far here.